Modern artificial intelligence models require massive amounts of data to be processed at lightning speed. While compute power continues to scale, the memory subsystem is hitting a wall. If you look inside a 2026 data center, you'll see the primary bottleneck. The processors are often idling, simply waiting for the memory to keep up. This happens because of how we have built servers for decades. A CPU is connected to its short-term memory, the RAM, through direct slots on the motherboard. This memory is physically locked to that specific processor, creating a hard limit on how much data the server can hold at once. To get past this limit, engineers are forced to buy the highest capacity DDR5 modules available. But as AI production drains the supply of high-bandwidth memory, the price of these 128GB sticks has climbed to the point where a single module can cost as much as a high-end consumer GPU. Relying on memory trapped inside a single motherboard is no longer just a design constraint. For the modern data center, it has become a major economic burden. This isolation creates a strange imbalance. You might have one server choking under a massive AI workload because its RAM is full, while the server right next to it sits idle with most of its memory unused. Because they are separate machines, that idle capacity is completely unreachable. This is known as stranded memory. It is a systemic inefficiency where expensive resources are trapped in place, unable to be repurposed where they are actually needed. The scale of this waste is massive. Industry data suggests that roughly 25% of all memory in modern data centers is currently sitting unused and stranded. For companies spending billions on AI infrastructure, realizing that a quarter of their most expensive hardware is effectively doing nothing forced a total rethink of how servers are designed. The solution is a protocol called Compute Express Link, or CXL. It allows memory to be connected through PCIe lanes, the same high-speed pathways used for accelerators, effectively moving the RAM off the motherboard's fixed slots and into the wider system fabric. As this server memory hierarchy shows, the teal CXL layer bridges the gap. It sits right between the fast, direct-attached DRAM at the top and the slower, locally attached SSDs, offering a high-bandwidth middle ground for massive datasets. With CXL 3.1, this enables memory pooling. Instead of isolated buckets of RAM, an entire rack dynamically draws from a centralized bank. When a server finishes a task, its allocated memory returns to the pool for the next machine. Decoupling these components converts RAM from a static, local part into a fluid resource that can be routed across the network on demand. The challenge with moving memory further away from the CPU is latency. Usually, moving data off the motherboard adds delays, making AI training and inference prohibitively slow. To solve this, Intel Xeon 6 uses flat memory mode. The hardware automatically manages the data, keeping the hot, frequently accessed information in local DDR5 while offloading cold, less active data to the CXL expansion modules. At the same time, the Linux kernel has evolved to stitch these separate nodes into a single, unified address space. This means the software simply sees one giant pool of RAM, so developers don't have to rewrite their applications to take advantage of it. In this Samsung flow diagram, the decode stage is memory-bound. Offloading the key value cache, which helps the model remember context, into the CXL pool, frees local GPU memory. This keeps the expensive GPU working at full capacity, instantly retrieving stored cache to generate the next token. By managing this data at the hardware level, engineers can scale memory capacity far beyond the motherboard's constraints, without breaking existing software ecosystems. This shift creates a massive economic advantage. Data center operators can now use CXL expansion cards populated with several smaller, cheaper memory modules to reach the same capacity that previously required a single, ultra-expensive high-density stick. When you add up the savings on hardware and the reduction in stranded capacity, this hybrid architecture results in a 60% reduction in the total cost of ownership for server memory, and the performance holds up under pressure. Testing from Micron on the 128-core Intel Xeon 6 platform shows a system pulling from both native DDR5 and CXL nodes at the same time. By interleaving the data across these paths, researchers recorded a 24% boost in read-only bandwidth and up to a 39% increase in mixed workloads compared to traditional setups. This is the beginning of composable infrastructure. We are moving toward a world where compute, memory, and storage are no longer locked in a box, but are modular resources that can be reconfigured in real time. CXL provides a technical solution to a physical bottleneck, allowing data centers to sustain massive AI scaling without the runaway costs of traditional architecture.